All right. Okay, very important announcement for programming test. The survey shows very divided opinion, half and half. About half prefer option 1, about the other half prefer option 2. So I will conclude, I'll make a decision. It doesn't seem like a vast majority preferring the alternative. So why don't we just stick to the original plan? Let's do that. I know it's not pleasant for Saturday, only once. Okay, right, confirm, no more change, no more confusion. But for the room, I will confirm with you very, very soon. I just want to double check with our computing manager to make sure it's there. Right, Saturday, 2 p.m. to 3:30. Oh, sorry, 3:20, okay, the time. All right, confirm. I'll write the e-class announcement as well. And for your project, I got one email about if I can find teammates. Have you guys all find the team members? If you haven't, could you please do the following? So I will try to end the lecture about 2 or 3 minutes earlier today. Come to the front. Either your team might need more member, or if you don't have a team just yet, come over. We'll try to see if we can make some team. Right? I'll try to do that today. At the end, just remember to come. All right? And as I promised to a good number of you back on Tuesday, I want to show you one example of compiler called LaTeX. Okay? And my slides so far, I'm not sure if you got a misunderstanding that I might be using PowerPoint. No, I use LaTeX only. I stopped using PowerPoint more than 10 years ago. So let me show you. I'll get to the point. And you will get a little bit of feel about what you might do for your project, which I'll release on Monday. I'm still debating myself. I got 2 projects in my mind. I'm not sure which one I want you guys to do. But this corresponds to a little bit to one of them. But anyway, just some example would be nice. Let me show to you. Let me start with the input. And I'll show you how the compiler runs and show you the output. Right? It's a nice example. All right, let's say I'm doing the lecture for lexical analysis over here. Okay? And in there, I got images folder. I just got the various diagram, pretty much like how you would do it in PowerPoint. Okay, let me show you this. Okay, this is just one of the diagram. Somehow it wouldn't open so quickly, but let me just try another one. For example, this one here. Yeah, for example, that's one of the diagrams you saw before in the lecture, right? But how do we write the slides themselves? Let me show you the source file, which is the input to the compiler, which would be over here, lecturebody.tex. Oh, sorry, let me just maximize that. No, I don't want to any updates. Let me do it again. There we go. And let me maximize it, all right? That's the source. That's how I usually create the slides. If I really want to see the actual products with animation, I need to compile that to the output. But let me just give you some idea. For example, this is one slide. I got some title of the slides. And itemize is one, you can think about it as more like a statement. I need to write like a programming language to say, now I want to start a list. I want to have some spacing. And then I say recall, some spacing. And this part here, say I want to include a graphics. And then I want to wrap it around some box, basically. Right? Things like that. I'll show you some interesting bit about how we do math. For example, here. This one here, for those of you who used LaTeX before to write a math, you will know what this is doing. They got a huge set of commands for you to use. For example, here, if I write / sigma, it's going to give me that sigma symbol. And do you guys know what this is doing? Yeah? Subscript. It's doing the subscript. But if I know superscript, I'll do, for example, this one here. Actually, I'm not sure how to say that. This one here. Anyway, just to give you the idea, and that's how I write the input to my slides. I never write like a PowerPoint, kind of style. Of course, they said for the PowerPoint, whatever you look is whatever people will see. But this one here, not really. Okay? Let me show you how it works. And normally, I will compile into 2 things. One is for the handouts, which is what you guys got from the website. Just basically one page, right? Each page. This presentation is the more fun bit. That one is gonna put animation. Oh, how does animation work? I'll show to you. There is a magic command called pause. So what does that mean? That means, let's say I'm presenting this slide over here. I say, now, pause over here. Once I hit, go to the next one, it's going to show just this part, and then pause again. Rather simple idea, but I would say from my end, there might be a better way to do it, but I simply just say lots of pauses to program the timings for the slides. Okay, let me show you how that can work, like a compiler. So now just remember the input here is more like a programming language with lots of syntax over here. But what about output? Output is going to be not something like, well, for example, a very typical way of using compiler. For example, you want to translate from Java into C, hoping that the output will behave just like the input. But the output you're going to see here is not exactly an input, just visualize output. Let me show to you. So it's a PDF, LaTeX. Let me just do the presentation one for you. Lecture presentation. It's going to do lots of stuff over here. Take a little while. Okay, let's wait. Once it is done, it's going to generate some PDF. That's the one I usually use to present. I'll just show you some little thing there very quickly. And then that's the example. But don't worry, it's not really like a, yeah. I think I'm pretty sure, well, I can tell you LaTeX is kind of interesting. You can still make things very pretty and fancy at the at the back end, like a PDF, but the input language could be very ugly when you write a code. Yeah, it's not very good design. I'm pretty sure I can write the code a little bit better. I'm pretty sure, but anyway. That's not something people would care. All right, it's done. Okay. Once it is done, what I want to show you is it's going to generate this lecture presentation PDF, right? Let me open that with, let's say, preview. And now you will see what I really meant last time about overlay. It generates 597 pages. I don't think you got that many slides, but how does it work? For example, you can see page 1, page 2 only show this. Remember the pause I mentioned? That's where the pause happened. And then they show just a little bit more. That's what I meant, overlay. So now if I do it from your eyes, it's like a PowerPoint animation. Input and output. That's a very classic compiler. Okay? If I decide to let you guys do project number 2 in my mind, this will be a little bit, you'll get a little bit flavor from this. Meaning that you got some input language, you got to design, you're going to do some visualization output of some sort, which would be nice. I'm pretty sure it'd be very nice to put on your resume or CV as well. Okay? I'm going to write the details over the weekend, and I'll release it on Monday. We'll see. But for those of you who might be interested in learning LaTeX, it's a fun tool to really use. Yeah, definitely, for sure. Good. Awesome. All right. For today, just a few topics to cover, and then very quick formal definition, and then I want to talk about how you can convert from regular expression to CFG, how you can convert DFA to CFG. Both are straightforward. And then I want to dive into more about ambiguity. Okay? If I can get there, I want to talk about a very famous example of ambiguity. It's something called dangling else. I'm not sure if any one of you heard about it. Dangling else. Anyway, hopefully we can get there. All right. All right, let's talk about formulation. I wouldn't trouble you guys too much, but let's now just do this one here. How can you design a context-free grammar for this? Right? This one here. I'll give you the solution right away, so I can also use it to present example for formulation. Start variable. So you cannot really have epsilon, so I can wrap around the epsilon by parentheses. Or it could be as many repetition as I like. Oh, sorry. What I meant to do was I can wrap as inside over here. I can have as many repetition as I like, and then, or epsilon, something like that. All right, that's one possible grammar, all right, for the context, for the language. And let's now go over the formal definition very quickly, okay? Let's now see, so it's like a DFA, we'll also get a tuple. So now we got 1, 2, 3, 4 components. Let's just go over that very quickly. So V will be all the non-terminals or variables. So if you want to also get used to non-terminals. And the terminals will be the symbols, alphabet, basically, right? So you can think about this is the terminal, this is the non-terminal. And obviously, you want to make sure they don't really mix with each other. That's why you will see on the slide, there is a condition over here to say they do not overlap, these two. All right? There's only one thing I would like you guys to figure out for me. Only one thing. I'll get there. Terminals and rules. You can see, definitely this is one rule. In terms of the rules, it could be S derives to this. Or it could be this derives to SS, right? So these are two example rules. And let's take a look a little bit more closely. Apparently, this particular one, both are just variables or non-terminals. This one over here is more like a mix of the non-terminal and terminal, right? Mix of terminal and non-terminals. So now if we want to formulate what a rule can really look like in general, we definitely should take this as a general form to be more accommodating, as opposed to saying it can only contain variables, right? Sometimes you might have some rule which contains only terminal, for example, epsilon. That's also one example. But, so here's my question for you. How do we say, formally, the set of rules? It's going to be a subset, meaning that we don't have that many, only the ones that are necessary. And the rule is going to be of the following form. V here is a variable, like S. A variable, or non-terminal. S over here is interesting. We call that a string. And the string here, as we can observe, it's not just contain variables only or non-terminals only. It will contain a mix of the variables and terminals. How can we specify the condition here to specify what V should be and what S should be? That's my question for you. I can give you the simple one. For V, it should definitely be just a member of V. That one's easy. What about S? What should that be? It would be wrong if you only say S is simply just a member of the variable. It will also be wrong if you say S is a member of the alphabets, the terminal. Both are wrong. They are not complete. But how do we? I give you one alternative. Would it work if I say S or can this work? I'm saying that either S is simply just a sequence of variables, or S is a sequence of alphabets. Still too restrictive. Agree? So that's also not good. We want a mix. This will have to do with our lecture before about specifying alphabets and strings. Anybody want to try? You raise your hand first, yeah. Okay, okay, did you mean V union alphabet? And okay, awesome. I'm pretty sure that's what you guys are thinking. That's good, exactly right. That's the only thing I want you guys to just make sure you can derive, right? That's the only thing. Might look a little bit weird when you look at that. Okay, good. And that's exactly what we have. I want to just show the formal pattern for derivation. And then we'll get to derivation a lot today, either leftmost or rightmost. We also need to talk about it. All right, so let's say we got U, V, and W. They're simply a mix of the terminals and non-terminals. And also we got one variable. And also we got a rule. Okay, so let's make it very general here. So this is a derivation, a single step. You can think about we go from A over here to W over here because we have a rule. A derives W. That's a rule we assume that we have. And then the left and right, UV, UV, they don't change. They can just be other mixes of the non-terminal and terminal. However, later on, when we talk about leftmost or rightmost derivation, the way you substitute the variable has to follow a particular order, which we'll see. Because the way you do the leftmost or rightmost derivation also can impact how we define ambiguity. We'll see. And this will be some special derivation, pretty much like the delta hat, if you remember, like a general extended version of the transition. This is to say, if we start with a string in the beginning, and we can somehow go to another string, this will be valid as far as the CFG that's given is concerned, if either just go with the same. That's kind of trivial. No rule should be applied. And this one here, you go to some intermediate one, and ultimately you go to V, right? Just to make sure you apply the rule for every step. Right? Pretty straightforward. And the final one, I'm just going to review. How can you define, given a grammar, it's a language? It will simply just be, okay, let's try to read. And this time you can see we only got sigma star, because when you talk about members in a language, there should be no non-terminals, only terminals. That's a final member in the language. No non-terminals. All right. And this is to say any string that's kind of reachable, I put in the quote, from the star symbol, meaning that you can derive, you can apply as many rules as you need to get to that string. And that string has no non-terminals, and that'll be a member of the language. All right? That's about the formulation. And you will definitely see that on the slides. Okay. Any question about this page? You okay, right? Good. All right, let's move on. And this one here is just about how you can instantiate the formulation. So you can also take a look. You can see the grammar will be all the variables, all the terminals, the rule, which will be here, and also the start variable, which is S. All right, that's also easy. And you can definitely make sure you can draw parse tree, but we're going to draw parse tree, quite many of them today. Okay, so this one here, I just want to mention, this is just another interesting grammar. If you recall from last time, let me bring you to the context. Remember we talked about version number 1 and version number 2. Well, one of the conclusions we made was both versions here are ambiguous, because there will be some string that can have two corresponding, or more than one corresponding parse trees, right? Because you can have more than one semantic interpretations. That's something we want to avoid, for sure. So we can now consider version number 3. All right, over here. For those of you who may have taken 2001, this might be quite ringing the bell, right? There might be something you have seen before, possibly. But anyway, so let's take a look. This string over here is something we mentioned last time, which can be used to prove that version 1 and version 2 are ambiguous. But this one over here now has only a unique parse tree. Okay? So what I want to point out, this grammar, we're still going to use the same grammar to do the leftmost and rightmost derivation today. So for this one here, I'll leave one thing as exercise for you. Exercise will be for you to draw the parse tree, which is rather simple. But we're going to see still several examples that will be very similar. Draw the parse tree, unique parse tree. But for now, I want to point out one thing to you as you study later. You ought to notice the following. You can see we start with expression over here, and we no longer put plus and multiply under the same variable. That's the key to make it not ambiguous. Because now you can see the plus and the multiply are at different level, meaning that they got different precedences. One has one's higher than the other. What you want to notice is this. Over here and over here. And different precedence. And of course, it kind of depends on the language you want to actually implement. Of course, our normal notion about multiplication and plus would be multiplication should have a higher precedence, right? It should be evaluated first. That's why we somehow put to say if you actually got a mix of the plus and the multiply, you have to make sure plus is done later before you actually can derive maybe the expression into term and also turn into multiplication, right? That's kind of the insight you want to have. Let's say we have another language. And if you actually want to somehow swap the precedence of these two, you should know how to do it. All right? So I'll write it down quickly. In this case, expression, the rule expression, and then we got expression over here plus turn. And we know that this expression over here can also be derived to turn, and then it can be derived to turn multiply factor. Turn multiply by factor. So this ensures if you actually want to do plus, you want to make sure you do the left one first, which has multiplication. So that means this will be done first. All right, that's one way you can interpret that. So this one here has higher precedence. In Antler 4, I believe, if you want to specify in terms of the operator precedence, either you can use this kind of style by creating more variables, or you can actually have some declaration outside of the rules to do that. You can definitely explore that option for your project if you want to specify precedence. All right, good. All right, any question about version number 3? That's the only thing I want to mention. If no, I will want to move on. Okay. Okay, so regular expressions to context-free grammar. Rather straightforward, but let's go over the principle, and we'll do one example and one exercise for you. I'll post a solution later, just for you to compare. Oh, by the way, we didn't really cover minimizing DFA this time, so it might come at some point. I think that's one very important topic. Just make sure you really know how to minimizing the DFA. All right, so let's now talk about principle very quickly. I'll just write it down here. So let's say if the regular expression is epsilon, you just have a rule like this, right? Just epsilon. Epsilon is considered as a terminal. If you have some symbol A, assuming that A is an alphabet, right? That would be just like that. And the way we do this one here for plus, we're going to do it recursively. Okay, let me write it down like this. We have a rule over here, and vertical bar means alternation, alternative. It's going to be either the context-free grammar, you can think about CFG here as like a recursive function, okay? The CFG of E or the CFG of F, meaning that you have to work out the context-free grammar for E first. Work out this, and then put an OR in between. That's kind of the idea, recursively. Right? For that one there, it's also very similar. It would be S, and then the CFG of E, and followed by the CFG of F. E and F. Okay? And what about this one? This one's similar. This one here will just be put it into parentheses. The CFG of E. Guys, what about this one here? What should be the corresponding rule? I got some regular expression E, and I want to take the cleaning closure. What will be the corresponding CFG? If you recall the semantics for E star, that means 0 or more repetition of E, including no repetition. That means epsilon is possible. So how would you write the corresponding CFG rule? I can start you with, for sure, you got epsilon. Henry. Concatenated with CFG? Yep, of E. Yep, I agree. I think for over here, I would say typically speaking, you wouldn't have to worry about either put in the left or the right unless there's some order that's required, depending on the application. But I think for this one here is fine for now, just conceptually, right? All right, that's a rule. Let's do one example. I'll do one, and then I'll leave another one that's a little bit harder for you. All right? Why don't we do this one here together? All right, this one, exercise. Okay? But they're pretty similar. Why don't you guys try for 1 minute, and then I will write down the answer. It's only a small topic, so once we know how to do it, we're done with this, and then we can move on to DFA. In case you are asked to write any context-free grammar in the test or the exam, you don't need to worry about the name of the variable. We can definitely tolerate any name. Okay. All right, presume everybody's trying. Don't peek. I'm going to write. Yep. Henry, would you agree? I might be wrong, so it might be nice if you check for me too. Thank you. All right, so you can compare. Oh, one thing I would like to mention, which we wouldn't talk about in the slides, unfortunately. As far as this course is concerned, whenever you want to come up with some CFG, you don't need to worry about minimizing the number of variables. You don't need to worry about. If you got more variables than necessary, that's okay. And there is actually a process. Not too sure if you guys heard about this. Do you know what CNF is? Normal form is right, Chomsky. Chomsky normal form, all right? I'll give you a little bit of background. If you're interested, outside the scope of this course, you can definitely look into. It is a theorem, or it's a claim. Every context-free grammar can be somehow turned into a normal form, which is called Chomsky normal form. And the Chomsky normal form has a very nice shape that will make it very easy for you to prove the pumping lemma of context-free language, just for your information. But I will not put it in the exam, don't worry. Only for your information, okay? Yeah, Chomsky normal form, it's good to know. All right, guys, exercise for you on the right-hand side. Good, okay, let's move on. Yeah, pretty easy. If I put a question on the quiz, it should be very straightforward for you. No trick. All right, what about DFA to CFG? There is certain rules you can definitely follow. I'll keep the rule on the slides, right? I'll just illustrate that right away using some simple example, all right? I'll do this one, and you do this one, exercise. I'll put it, excuse me. I'll also post a solution for you later, okay? The idea goes as follows. The number of states in the DFA correspond to how many variables you want to have in a CFG. In this case, we can just make it the same name, S0, S1, okay? So we have S0 and also S1. And which one should be the start variable that's put on the top? Well, depending on which starting state it is. We're assuming that it's only a single start state for our DFA. So it should be OK. Right, so this will be S0 will be the start variable. And then you want to derive the rule. And I would suggest try to handle first which state is the accept states. If it is the accept state, that means you don't have to derive any more string or character afterwards. The current one is the terminating case. You can just stop there. So in this case, S1 is a accept state. I'll just put epsilon. Put an epsilon whenever there's a accept states. And what about transition? Well, for example, you go from S0 to 0, you go to S1, right? So that means 0, S1. Or if you go for 1, you go back to itself. It will be 1 and then S0. And for this one here, S1, take 1, you go to S1. You take 0, you go to S0. That's it. Very mechanical. It can definitely be done in a way that's similar to what you did in assignment number 1, to convert, right? All right? To make sure you really feel comfortable, exercise. Do it, and then I will give you the answer to compare. All right? Exercise. All right? Good. Any question so far? Okay? Yeah, as a promise, I should really end about 3 minutes or so earlier to help you on the team. So let me just go for another 3 to 4 minutes. And I would say to really do that, how about this? I'll do the leftmost derivation properly on Tuesday. Why don't we start with the interesting bit first? You guys feel free to pack up, that's OK. But I want you guys to look at this grammar here and think about it. We can have some very quick discussion. Give me a moment. I'll get there. But we got some stuff to go over quickly on Tuesday. Oh, just give you some very quick look ahead. For next week, what I plan to do, at least for a good part of Tuesday and Thursday, I want to distract ourselves a little bit from parsing. I want to talk about the visitor design pattern, which might be useful for your project. So for those of you who are not exactly sure how the visitor works, I can talk about it. We can learn it. Since 3311 is not really required for this course. All right, guys, here is a question for discussion. All right, we only take 3 minutes. I want you guys to look at this grammar over here. And of course, we haven't really formally defined what it really means to be ambiguous. But very easy. If you can find any string that can have different parse trees using the rule, that means the language is ambiguous. Based on this, can you see whether or not this grammar is ambiguous? Of course, since I'm asking you, it's got to be ambiguous. But now, your job is to find some weakness. Before I point to Henry, I want to see if anybody, before I have to point to Henry, because he's so eager to let us know, which is good. You want to say? Yeah, go ahead, please.
Well, if you stop after the statement in the first part,
yes,
and there's still an else after that, like there's no way, if an EXPR then statement, then you satisfied 1,
yes.
and you don't need to keep going to 2, but you could if there's an else there.
OK, that's good. But of course, you're just describing a rule, like alternative. I can tell you the key thing about proving that this grammar is ambiguous is about the second one. Something about the second one. The else. Matthew?
I'm assuming we just take the first option and then stick it right after the else, so we'll have else. So that's second statement. And second options.
Mm-hmm.
That would be the else statement. And then be replaced with if expression then statement.
OK, maybe. Let me conclude today just by the following example. This one here. Let me just give you intuition first. We're going to dive into it a little bit more deeply on Tuesday. Okay. If you have a program like this, you say if then, if then, and then else. It is so-called a dangling else I mentioned in the beginning. You guys should know about dangling else. It's a CS major, okay? Dangling else, okay? Why is it called dangling else? This else guy over here is very poor. It can either belong to the if over here, or it can belong to the if over here. It's ambiguous. Somehow, we can have two parse trees to show that. That's what I want you to know today. And I'm going to post the slides. You can take a look. OK, now this is what I need. If you either need a team or your team don't mind accepting other members, please come forward. Let's do this only once. Come forward.